Hi all. We are ready for the next talk. That the new speaker is Alexandra Koulouri from Tampere University, and she will talk about skull conductivity and focal source imaging from EEG recordings with the help of Bayesian uncertainty modeling. Please, Alexandra.
Hello.
Very long title, but it's okay.
I will share the screen and my presentation. I hope you can see it. Yes, it's going to be a little bit mathematical, but I hope I will be on time.
Sure, anyway, okay. Otherwise, I'll appear to say, okay.
That's it, yes, something like that. Okay, hello
okay,
everyone.
Thanks a lot.
I hope you are fine, either at home or at your office, I don't know. Anyway.
Yes, thanks a lot.
Yeah. For researchers who are working with inverse problems, we know that actually the knowledge of or having actually an accurate observation model is quite crucial in order to get very good estimates, or quite good estimates often. But in reality, many times what we have to do is actually to use a generic model, or to put heuristically some parameters in our modeling and solve our inverse problem. So in this talk, I will focus on a problem related to the source imaging, reconstruction of brain activity using EEG recordings, where in our modeling, we don't have access actually to the skull conductivity. I will show you an approach, a Bayesian approach, mathematical approach that have been used previously in other inverse problems. And in the second part, I will also try to explain a little bit an approach that we try to develop recently, how to actually estimate the skull conductivity in addition to the source locations using EEG recordings. So very, very briefly, what is EEG source imaging? Most of you already know, but I just put it here just in case. So it's the reconstruction of brain activity in a bound domain. This can be the gray matter, deep source, or whatever we are interested in, using the EEG recordings. The computational model often used, I would say, it's I will have here in this presentation is a distributed source modeling, where we have fixed location for the dipoles, and we connect them through a mapping to the EEG observations. This mapping is called Litfield matrix. You talk a lot, I guess, today in the morning, especially how you can build this using finite element methods. The main problem we have in this case is that M, if we call M the number of measurements, and then the number of unknowns, we have far less measurement than unknowns, so we have an undetermined problem. So a huge problem is that different source configurations can explain the data, the observation that we have. And the second thing is we have really, our system is very fragile with respect to noise. So just a little bit of noise can cause a big problem. And here I have, I like this figure actually that I put together all the steps that we need to follow in order to design an EEG algorithm. And the first part is actually to create a nice forward or observation model. And after to plug some prior information, physiological or whatever we consider important for the particular case. But in this part here, in the observation model, we need to have idea what is, actually we need to know what is the head geometry and the tissue conductivities of the person that undertakes the examination. After we plug the EEG recordings, and we try to localize where is the activity, hopefully. And we have huge variation about the geometries, of course. I mean, everybody has totally different head. There are quite laborative ways to using CT and MRI to extract this. And I think they have done pre-surfer and all these people that develop tools quite nice work. I want to say that I want to say that the one difficult aspect is the determination of the electrical conductivity, so the different tissues, and I will focus especially in the skull conductivity tissue because it has very large variation from person to person, and it can really significantly affect our reconstructions. And here I have an example that probably you can see that we have a red arrow here that shows the true location of the brain activity, presumably it's a simulation. And we have two reconstructions, one in blue and one in green, where in the blue case we have underestimated the skull conductivity, so we have taken lower conductivity, underestimate higher conductivity than the actual person. In the other case, we have underestimated. It means that we have taken lower than the actual we have considered that the person has, and in the second case we have overestimated. So we see the displacement of the source in this simple example. And the solution can come from the Bayesian approximation error. And this is a nice concept and method that was developed from Jari Kaipio and Somersalo many years ago and has been used in other inverse problems with success. And we tried to embed it in the EEG source imaging problem. So I don't know if we have talked already about inverse problems in this workshop, in the inverse solutions in this workshop, and related to the Bayesian concept of solving inverse problems. But I would say that the idea is to basically, when we solve an inverse problem using Bayesian framework, we are interested to estimate the posterior, and this is of course proportional to the likelihood function times our prior. And in this talk, I will focus mainly in the likelihood part, the likelihood function, exactly because the likelihood comprises information about the lead field and our assumed or selected noise model. And in the Bayesian approach, the key idea is to build a simple observation model using, for example, a standard lead field, a standard lead field which has some literature values, for example, for the skull conductivity, but also to incorporate an additive approximation error term that you will use it to compensate this simplification. And in the next step is actually to build a model for this approximation error. And to do that, usually you use learning techniques or training techniques. For example, you build a training set of lead field matrix that they have different conductivities, sample from a distribution, and then check the errors between your standard model and your training set, and you estimate this error. And from this error, you use the statistics and you plug them in your standard likelihood model. And this hopefully, with this, if the training set is good and includes good information, then when you try to do real experiments, you go to a patient, you hope that the characteristics or the unknown parameters that the patient has are somehow included in this training set. And then basically you create a more reliable likelihood, in effect, which results also in a better posterior compared to using a standard likelihood that doesn't include any information related to possible errors and uncertainties. So a little bit, a little bit about some more simple mathematical things. So here we have the accurate, presumably accurate observation model, where we have U the potentials equal the lead field matrix A. Here we have in parentheses sigma skull, which denotes the skull conductivity, the parameter that we don't know actually, times J, which are our currents, and plus the noise, which is additive noise. So in Bayesian approximation, we modified this thing, and our model is slightly different. And basically, we substitute let's say true lead field with a standard lead field that has this sigma 0. This could be from the literature. We can pick the value, and we have here this epsilon, which is the difference between actually the difference between the results between the standard and the true model, and plus the noise. And what we do after is something that is very, I would say, standard in Bayesian statistics, is basically to derive our likelihood, which is given from this integral here, very simple, and given the so-called, I call here extended observation model, we can see that the probability of the observations, basically given the total noise, which it's the nu here equals to epsilon, which is our approximation plus the noise, measurement noise. It's just the Dirac delta function. We plug it in, and what we have is that the likelihood function is equal basically to the probability of the total distribution of the total noise. And up to this point, there is no any, I would say, any approximation or any assumption related to how this should look like, this probability. But in the next step, we need to have an explicit form. So we need to take some. We need to take into account some approximations. And the obvious is for the noise, the measurement noise, we can have Gaussian noise. I mean, this is pretty standard. And for the approximation errors and the dipole distribution, so for the epsilon J, we consider joint Gaussian, which actually, I would say that it's in this particular problem is a good approximation, because we see almost linear relationship between the sources and the errors. Higher, so let's say sources will result in higher error. And then we derive the conditional. Since the joint distribution of epsilon J is Gaussian, also the conditional of the approximation error is Gaussian. This notation here shows that we have epsilon star is the mean and gamma epsilon is the covariance. So the total error has a Gaussian distribution. Very nice. They are mutually independent. So we have the mean is the sum of them, and the covariance is the sum of them, of the two covariances. And then we have the approximate likelihood, which is given by this lovely symbol expression. And of course, it's a little bit more complicated, the conditional mean of the approximation and the covariance, but you can find details how you can go from the joint J and epsilon, joint Gaussian, to the conditional, for example, in the book from statistical and computational inverse problems, and you get this form. And very nicely, after we use this likelihood, we plug it in our Bayes rule, so we have our posterior here. And often what we do is we don't estimate posterior distribution. This is a standard thing. We use a point estimate. Here I have written the maximum posterior estimate that is given by this formula here. And what we need to know actually here is in order to be able to solve this problem, actually, is we need to have an idea what is this approximation error mean, the mean value, and the covariance matrix of the approximation error. And this we can do it using some very simple simulations, which I will give in the following here an example that we apply in this paper with Willer and Vilainen in improving source localization with brain uncertainty modeling. What we did, it was basically we assume a Gaussian distribution for our skull conductivities, and with some limits that we took from the literature and some mean value. We exclude also any outliers like some very small or very large or something if it was negative. And what we do with this, we took samples basically from this Gaussian distribution, and we plug them, the samples for the skull conductivity, and we created the corresponding lead field matrices for all these 200 samples. Also, we took samples for the source configuration, and we estimated these approximation errors. In the final step, basically what we had to do, it was very straightforward, just to take the statistical mean and covariance based on the samples. And in the next, I have a result. I have included only one result related to this paper that we did at the time. And what goes about this paper was we have a, and what do they mean, these figures? Is that we have a true skull conductivity of this value 0.014 Siemens per meter. And in our reconstructions, we use a standard lead field with 0.1855 Siemens per meter. And what we saw here is basically the difference between in different locations, these are different source locations, and the box and the triangles, and each location shows if there is improvement or not when we use or we didn't, when we use the Bayesian approximation or approach in our solution. So basically the square here, for example, shows that in this location, we didn't see really improvement in the source localization when we use the standard model without the Bayesian approximation and with the approximation. And the triangles that they are pointing upwards, they show actually when we, in the locations that we had improvement in the source estimates when we incorporate the statistics of the approximation error. And we see here for low noise, SNR it was 30 dB, that was quite good for many cases, especially for cortical, I would say, superficial sources compared to some deep ones that we didn't see improvement. And in the second case, we have low increase in noise. One thing I want to pinpoint is that the Bayesian approximation or the approximation errors would work optimally if the noise level, the measurement noise, is quite lower than the approximation error level. And this is actually, I think nowadays is tractable because, for example, we can repeat many measurements, many tests, and averaging out or canceling out some of the measurement noise. So that was the first thing here. And but at that point we start thinking, okay, this is nice, but can we estimate also the approximation error, the error term, this epsilon, and also can we extract any information about the conductivity part? And it was this nice paper from Nissen and Kaifield and Kolekmainen, that gave us this intuition. And actually, they were saying that the approximation error can be estimated if it can be expressed, if it is simple, actually, if it can be expressed by few basis functions. And also how this basis function can be picked. They can be picked basically by applying eigenvalue decomposition in the numerical covariance matrix of the approximation error. So the approximation error, the covariance of the approximation error that we have estimated previously using simulations, we can actually use exactly this thing in order to build basis functions that can actually describe this approximation error. And then our extended model can be a little bit actually the approximation error in the extended observation model can be further decomposed into epsilon prime and epsilon prime plus the mean of the approximation error. And actually this epsilon prime is the one that we want to estimate because it includes exactly the majority of the useful information of the variation of our approximation errors. So here we have this epsilon prime is W alpha, where we have P components and less than M, which is the total number. And okay, and what we did next basically is the thing that also it goes in that nice paper. We estimate the likelihood by marginalizing over only the noise and the second and the nuisance approximation error term. So, so we got something like that. Our likelihood had this form. We left intact the epsilon prime, the main one, and we were interested to estimate at the same time the noise, the current J and the alpha parameter, which would give us an approximation of the modeling error epsilon prime. So by using, for example, map estimate, we can estimate these two, the current and this alpha parameter, and then we can extract what is the value of this epsilon prime. So we can get an idea what is the level of our error. But the question we have is, how is it possible that our conductivity is related with this epsilon prime? Or are they connected or not at all? And we say that, okay, we can estimate the conductivity, the skull conductivity, if most of the information of our approximation error is related to, of course, this the skull conductivity. And so what we did is we just took the approximation error definition here I have, and we applied Taylor expansion to this around the linearization point. I haven't included this equation, but it's quite straightforward. And after we estimate also the covariance of this, based on the Taylor approximate expansion, we estimate the covariance, and we saw that, okay, the covariance of our approximation error depends on J, or our current, and also on the skull conductivity. But actually what we saw, especially from simulations, that this error, the covariance of the approximation error depends really strongly on the sources. And that was a little bit disappointed at that point, because we felt, okay, it doesn't have enough information to recover the skull conductivity. And so we thought that, okay, to reduce the effect of source locations in the approximation error, we can consider dependent error covariance for each source location. If we do that, we can see actually that the error, the approximation error related to single locations, it's actually the covariance of these errors is proportional to the variance of the skull conductivity. Very simple thinking concept. And that was good because then we could combine with the algorithm like the dipole scan algorithm, and we could estimate a pair J and alpha. So we could identify a single location where we have the highest activity. And based on that, we could have an approximation error with respect to this location. And we could use then this approximation error at this location to extract actually an estimate for our skull conductivity. And that was good based on our results. Simple test, I would say, but yes, we did some very simple tests that I have them here. What we did is we considered two cases of true conductivity, 0055 and 011. Here is a standard conductivity, which it's higher. So it's overestimated in this case in the first line, and in the second line underestimated. And we reconstruct, we use this simple maximum likelihood basically to reconstruct the source location. Here it's the two cases, and here not only the location but also the conductivity value. And our results actually about the conductivity estimate was quite close to the true one. And also we saw here in the second case that we have underestimated conductivity. Also the Bayesian approximation approach, this have given better estimate with respect to the reconstruction. Here is the Euclidean distance basically of the true and the estimate solution, very simple. And so the benefit of estimate this single value bulk conductivity is it can be in this way. It's actually, this can be used as a calibration step for the patient under examination. The good thing is using EEG recordings to estimate this skull conductivity instead, for example, of injected currents. It is that we don't disturb actually the brain. We can do it very simply by performing some control EEG tests, for example, using somatosensory potentials that we know roughly where is the brain activity, and use dipole scan combined with the Bayesian approximation estimate a single value for the conductivity, and then plug it to other models, other tests for this particular patient, or try to do transcranial direct current simulation, for example. And so I will conclude saying that the Bayesian approximation allows to treat statistically unknown or uncertain model parameters that are not of primary interest, but are quite important for the accurate localization of the brain activity. And so that's good. And second thing is we can use this approximation or statistics under certain conditions in order to extract information for a known parameter like the skull conductivity. One thing that I want to pinpoint related to all this is that the Bayesian approximation approaches nice as a concept, and I think the important part in the whole thing, which is the effortful part, to make it more broadly used is the fact that we need to build quite good training sets and learning methods. For example, people who are working with implementing good forward models in EG, I think, and other people that they are working with automation of the segmentation and creation of the meshes, for example, of EG and this, are very, very important, their work, in order to create very good databases that we can use actually to estimate this type of errors and use them later in a software, for example. And I would like to say also that these the publications that are related to EG source imaging, Bayesian approximation, I have summarized it here. They're related to what we have done. Up to now, it is we did one work related to the head geometry uncertainties a long time ago. And now we have focused in the skull conductivity related uncertainties. In the latest work, we tried to estimate also this bulk skull conductivity in addition to focal sources. Previously, with collaborators like Luca, Kaipio, Walters, we tried, and Rimbilainen, I forgot him. We tried to use the Bayesian approximation error and approach to improve our estimates and to show that indeed they are improved, the source localization errors are reduced. And I think that's it. These are my contact details if you are interested in this type of problem. And thank you very much for everything.
Thanks a lot, Alexandra. It was interesting, and you were in time that you were worried, but okay. So we see if there is some question.
Yeah, of course, cannot see anything.
Okay, Alberto.
I was very fast as well.
Okay, can you unmute? Sí.
Yes, thank you, Alexandra. Very, very interesting talk. So if I kind of missed the first part of your presentation, but if I understood fine, you basically have an estimate of the variance of the forward problem by putting variance on the conductivity parameters. Yes, of the inverse based on the forward. Is that correct?
Yes, the idea is basically you when we say forward, I mean, we don't know, let's say that what these are the conditions of a patient that we have in our lab. But if we have developed a nice database of lead field matrices, for example, and using really creating very good forward models and estimating an error between these forwards, the training set, and our standard model that we the software of our, for example, EG device, let's say, has, then we have the possibility to reconstruct more reliably the source activity. That's the idea, basically.
I was just wondering whether you do already have like a database of conductivities so that you can have their variances.
Yes, you can how you do it is basically
so from a database, or whether
the conductivity values people have based on their age and their gender, and these they have different values, let's say, in this. Now, I mean, ideally it would be nice to have different database. Okay, I don't have a database of conductivity. I have assumed that they follow Gaussian distribution in this, to be precise and to answer your question. But ideally, I would say that what you want to have is to have an idea about how the conductivity of different age groups, ethnicities, and this, they have what is the curve. So you can sample them. And then you can create database of lead field matrices for all these different people, actually. Groups of people, and then based when a patient comes, in your lab, you know which one, let's say, which statistics to plug in your device in order to get a more reliable result. That's, for me at least, optimally, it makes sense. I don't know.
Yeah, it does. It does. Thank you.
Yeah, thank you.
And also, Alexandra, can you include also uncertainty for the other conductivity?
Yes, actually, that's possible. I mean, you can add whatever, all the possible.
Yeah.
Yes. The thing is that we thought that the skull is a little bit more, it has a little bit more stronger effect actually than all the other. And the CSF actually pretty, and not only a stronger effect, has strong, also greater variation from, between different patients compared to, for example, CSF that pretty much we know that its value it's the same for everybody. I hope at least.
Okay.
That was, but yes, you can include other uncertainties. Yes.
Okay.
Yeah.
Thanks.
Other conductivity. Yeah.